So in this video, we will be looking at restrictions of logarithms here. So restrictions on logarithms basically come from the restrictions that we looked at for exponential functions. So for exponential functions, I'll just move this to the side here. We have y equals some constant to the power x, and we have some restrictions on this base c. As a result, in the inverse function, y equals log base c of x, we're also going to see some restrictions for this particular base for our logarithmic functions as well. So for y equals c to the x, this exponential function, we can have all sorts of bases, right? We can have 100 to the power x, that's totally fine. What does that look like? It looks like an increasing exponential function. Totally great, we get this exponential curve here. We could also have y equals 1 over 100 to the power x, that'd be totally fine. All that would happen is that we get this decreasing exponential function, decreasing curve here. And but the thing is, we wouldn't be able to have something like this. We wouldn't be able to have y equals -3 to the power x. And there are, you could say more technical justifications for this, but really, I encourage you to plug numbers in and get numbers out for x and y, and I encourage you to plot them onto a two-dimensional coordinate grid, x and y here, and see what you get. I'll give you a little bit of a hint here. If you plug x equals 0, you'll get 1 out, right? So we'll have this point, this y-intercept. If you plug 1 in, you'll get -3. So for 1, you'll get -1, 2, and 3. So you'll get this point right here. If you plug 2 in, you'll get 9. So if you plug 2 in, you'll get 2, 3, 4, 5, 6, 7, 8, 9. So this is definitely, as you can see, an improvised graph. It's not very beautiful at all. So you could say, oh, this gives me some function. It just seems to like oscillate or something. So it goes down and then up, and so we connect these curves, and maybe the next one, for the next input of 3, we're going to have a negative value again. So maybe we just go down or something, and then we'll go down to -27, and then we'll go up to +81. And what's the problem with a function like that? And the problem is we can't connect these lines like this because there's going to be a whole bunch of undefined values actually. So think about what it means to raise -3 maybe to another value. So if we take -3 and we plug in, let's say 1/2. If we plug 1/2 in, there's no answer there, right? So we would have a bunch of holes in this graph as well. And so we get this, we can plug numbers in and get numbers out, but when we do that, we don't get either of these nice, what we call exponential curves. We get somewhat wilder behavior, and so we just don't call that, we don't call them exponential functions because they don't exhibit this exponential behavior. We don't get exponential curves out of them. So we say we don't like functions that look like y equals c to the x where c is negative. So we say c has to be positive, right? That's why we have this restriction. We want an exponential function that has a nice exponential curve. And if we plug in if we try some sort of exponential function with a negative c value, then we get something that is not exponential. It doesn't have this exponential function behavior. Okay, so let's look at another c value that we avoid. So another c value that we avoid is 1. We don't like bases of 1. Now, why is that? Well, the reason for that is because if we have a base of 1, we also don't get this exponential behavior. So let's try y equals base 1 to the power x. And let's plug in some numbers and keep track of them with a table of values. So hey, let's plug in 0. I get 1. If I plug in 0, I get 1. So I get this same y-intercept here at 1. Let's plug in 1. Oh, 1 to the 1 is 1. So I get this other point of 1 and 1. Let's plug in 5. Oh, I get 1, right? So 1 times 1 times 1 times 1 times 1 is really just 1. So plug in 1, 2, 3, 4, 5, I get 1. No matter what I plug in for x, actually, I'm just going to get 1. No matter what I plug in for x, all of my outputs are going to be at 1. So this would be the graph. So this is actually the graph of y equals 1. Right? It's a linear graph here. So it doesn't show this sort of exponential behavior either, right? We don't get that exponential increasing or decreasing curve. So we have these restrictions on our bases so that we get, you could say, so that we get interesting exponential functions. Obviously, this is not, the most technical way to describe it, but that's the essence of it. So we have these restrictions on our bases for exponential functions, and so as a result, for when we take the inverse, we're taking the inverse where our base has these restrictions, and so the base will carry those restrictions with it. So for logarithms, we carry those restrictions for our bases as well. Now let's also look at x here, about what values we're allowed to plug in. So for the values that we're allowed to plug in to our logarithm, we can think of what values we're able to get out for our exponential. So for our exponential functions, let's say for y equals c to the x, where c is positive, sorry, c is always positive. Let's look at y equals c to the x, where c is greater than 1. These will be increasing functions. They all look like this, and we have an asymptote. Right? We have an asymptote for these exponential functions. The function, no matter how negative an x value we plug in, the function will never hit 0 as an output, and it will never hit negative outputs. So all of these outputs are impossible. So for the range of y equals c to the x, where c is greater than 1, y should be greater than 0. So that's the range for increasing exponential functions. Let's look at decreasing exponential functions for y equals c to the x, when c is some value where we get a decreasing function. So anything in between 0 and 1 we could plug in as a base here, and we would get this decreasing function. Well, we get the same range here. We get the same range for our exponential function. Now, what happens when we take the inverse of this exponential function? Well, we get a logarithmic function, and the domain of that logarithmic function is derived from the range of the exponential function. Therefore, the domain of your logarithmic functions should only be positive numbers. So for y equals log base c of x, the domain, let me include that, the domain is that x must be greater than 0. And obviously x should be a real number, and c should be a real number. So so the base can be any real number that is positive and not 1, and the input can be any real number that is positive. And that's I'll show you what those look like. So these are the restrictions. These are the restrictions that we have for logarithmic functions. Hopefully this look at the restrictions on exponential functions has made it clear why we have these restrictions for logarithmic functions. Looks like kind of a mess. I could have done a better job here, but I have summarized these restrictions here in this box. These are our restrictions for logarithms. And that's sort of all explained here as well. Now remember that logarithmic functions are the inverse of exponential functions, and as a result domains and ranges are swapped, which is why we get x greater than 0 for allowable inputs. And the following table explicitly illustrates the relationship between the graphs of these two inverse functions. So the basic properties of our exponential functions is that there is a horizontal asymptote at y equals 0. Conversely, the basic property for the graph of your basic logarithmic function is that there's a vertical asymptote. Rather than a horizontal asymptote that we have for exponential functions, we have a vertical, an up-down asymptote at x equals 0, which makes sense, right? We would swap domain and range, and we would swap asymptotes from horizontal to vertical, because everything that was usually associated with y will now be associated with x. So for the basic properties of exponential functions, all graphs go through this y-intercept at 0 and 1. Hey, could you guess what that would change to for logarithms? Well, it wouldn't be a y-intercept, that's for sure. It would now be an x-intercept. So all logarithms have this x-intercept, right? The y-intercept will now become an x-intercept. We will swap those coordinates. So 0 and 1 will become 1 and 0. Now, there are also some basic properties that both of these functions share, and that's with respect to the base. So when the base is larger than 1, and we have an exponential function or a logarithmic function, they will both be increasing functions. So if your base is larger than 1, you have an increasing function. If your base is in between 0 and 1, you've got a decreasing function, whether it is exponential or whether it is logarithmic. So there are some properties that they share, and the properties that they share depend on the base. But everything else, like the horizontal asymptote, switches to a vertical asymptote, and the y-intercept then becomes an x-intercept once you swap those x and y coordinates. So let's look at a basic logarithmic increasing function. So for y equals log base c of x, where c is larger than 1, your base is larger than 1, this is what your increasing logarithmic function will look like. And let me just restart here. There you go. So this is what it will look like. Let's actually do an even better job of this because I have a plan for this particular graph. There we go. So this is what your basic increasing logarithmic function would look like. To get this result, you would need a c value larger than 1. And for a logarithmic function with a base that is in between 1 and 0, then you would get a decreasing logarithmic function, and it would look like this. And if you take your logarithmic graph and you rotate it, if you rotate your logarithmic graph, you would see that this looks quite a lot like an exponential curve. And it is. It's just an exponential curve that has actually been reflected. So telling you to rotate it isn't necessarily the best advice, although you would still see an exponential curve. But the best thing to do to see the relationship between logarithms and exponents is to reflect them. How would you reflect them to see that relationship? Well, you would reflect them about the line y equals x. Because all inverse functions, if you look at their graphs, then their graphs are essentially transformations that you can describe as reflections about the line y equals x. So here, if I wanted to draw the exponential function that would correspond to this particular logarithmic function, right? What would the inverse of this function look like? Well, it would just look like an increasing exponential function. So here we have an increasing exponential function. This would be the inverse of this particular logarithmic function. So for y equals log base c of x in red, here in black, we would have y equals just base c to the power x, c being greater than 1. So we have this inverse relationship, right? This red curve is this logarithmic curve. It is an identical curve to this exponential curve. It's just that it has been reflected about this line y equals x. And the same goes over here. So here we have y equals log base c of x, where we have a base in between 0 and 1, so it's a decreasing function. And what would the inverse look like? Well, it would just be y equals c to the x, where c is in between 0 and 1. And it would be a decreasing exponential function. And in this particular graph, we can see that there's also an invariant point on that line of reflection, and that will always happen for inverses. So here we can see that there is an invariant point. Right? That is a point that doesn't change after the transformation. This kind of looks like gibberish, so let's just fix that. There we go. There we go. So that is the relationship between logarithmic functions and exponential functions. And here are our first logarithmic curves. We have an increasing curve on the left and a decreasing curve on the right. And another thing to notice is, let's use a different color here, is that for our exponential function in black, we have this horizontal asymptote, but for this red function, we have a vertical asymptote at x equals 0. And for this red function, we also have a vertical asymptote at x equals 0. So hopefully that's instructive to look at those curves and to see the relationship between those logarithmic curves and their inverse curves, which are these exponential curves. In the next video, we're going to apply this, or we're going to leverage this relationship between exponential functions and logarithmic functions to solve a problem.